Hello folks, in this little video we're going to take a look at problem 3 from activity 1. We'll make our little NEMA diagram here. And our ladder logic program, right? So for this problem we have a conveyor belt that sorts items. Alright, so our little conveyor belt here will move items along its track, and if it detects some kind of metallic item, right, which will have a little Hall effect sensor sensing that, it'll use a motor, right, another motor, maybe I'll use green for that, to kick that little item off of the belt. Okay, so first thing we want to do is make a little shopping list. Right, we'll go ahead and come down here, and I will make Tias's shopping list. So, looks like we want a start and a stop button. So, 2 buttons. This just gives us information on how the start and stop button needs to behave. This next one here tells us we need a Hall effect sensor, and the NEMA symbol is the same as a switch. So we'll say 1 times Hall sensor. If this is your first time hearing of a Hall sensor, this is basically a is this a metal object sensor, right? Our Hall effect sensor uses a magnetic field, right? Kind of like one of those like treasure hunter things, right? Beeps whenever they find metal, right? That's a Hall effect sensor. Except instead of beeping, we're going to use a motor to kick something off of a conveyor belt. So we know we need a Hall effect sensor. If something metallic happens, the motor boots the item off. The motor will stop when there's no longer something metallic. And the motor doesn't engage if a normally closed switch is overriding the setting. So we also want 1 times normally open switch. Okay, 4 components. So, just so we remember our little diagrams, let's recall how we draw these. And it occurs to me that we want to specify that these are normally open buttons, right? And I think I wrote that wrong. This is a normally closed switch, sorry. Normally closed switch. So, just so I have the reference here, right, we remember from our little NEMA reference table, normally open buttons are drawn with our T upside down, right? Remember the spring is kind of pushing up, so if it's normally open, we draw the T on top of the 2 contacts. Our Hall effect sensor, we're told, looks like a NEMA switch. Remember, this guy is opposite, so normally open is going to be down like this. And our normally closed switch, since it's normally closed, will be resting on top of the 2 contacts, like this. So we need 2 of these, 1 of these, and 1 of these. We remember that all of what we're about to draw in this area, right here, right, is essentially some 24-volt line that goes to our device, right, whether that's a switch, a button, a motor, whatever here, right, that goes into one of our PLC, an X or a Y, and then out of our PLC, right, through the common, goes back to the 0 volt. This right here, is essentially the circuit that we're going to implement over and over. Also occurs to me that on my shopping list I've forgotten two very important items. 2 motors. And again, we're just going to use our starting coils to represent these motors, right? Which can be drawn with circle with the letter M times 2. So 6 components in total. All right, first let's start with our buttons, right? Start and stop button. It's probably a good place to start. Well, a better place to start be providing power to my terminal blocks. And so this guy is 24 volts, and this guy down here is 0 volts, right? So we're essentially building several loops that start from here and should end up in here, right? All right, so starting with our buttons, we will connect those to, let's say, X1 and X2, right? These are our inputs, so I'll go ahead and draw my little contacts here. We know these are normally open, so I'll have one here, another one here. Connect this one to X1, connect this one to X2, right? We also know that these should be going to positive 24 volts. So I'll draw a little connection down here. Actually, maybe I'll go up and over. Straight up like this. And this guy also needs to go to 24 volts, right? So we have our current coming out of our 24 volts, right? Traveling up here, goes through this button, or through this button when they close. A minor note, see if you can predict whether this is sinking or sourcing, right? Current is coming through these buttons, and if you said these are sinking, you'd be correct, right? Our current is sinking into the inputs. We also remember we need to connect our ground terminal back over here, just arbitrarily, there we go. That's our 0 volt line coming out of C1. So we've got our 2 normally open buttons. Let's also connect our switches, right? We've got a Hall sensor and a normally closed switch. So I'll come over here. I'll draw my normally open, right, or the Hall effect sensor here, and then my normally closed switch. Oh, whoops, that's wrong. We'll say if this is my Hall sensor, it's got to be below and above for my normally closed switch, right? And we'll go ahead and do the same thing here. Take this guy, wire it to positive. Take this guy, wire it to positive. We'll take this guy into X3 and this guy here into X4. Right? So now we've got our 4 switches. So, sorry, 2 buttons and 2 switches. Finally, we need our outputs, right, which is 2 motors. So I'll go ahead and let's just choose Y3 and Y4, right? We will also say these will be syncing, so I'll have my, maybe we'll make these green. We'll have our motor here, and just for clarity, I'll call this one MC for motor conveyor, and I'll call this one M for the motor that boots stuff off, right? So we'll connect like this, and lead that to positive. Excellent. Now we're missing one more connection here, right, which is our common. C2 must also go back to ground. So go ahead and take that, come over here, and plug that into ground, right? Again, all of these circuits are essentially a repetition of this. We're coming out of 24 volts, into some kind of component here, right? Could be a button, could be a motor, could be whatever. That's then going into our PLC's I/O ports, right? Either our X's or our Y's. The book sometimes represents these as I:1, or our outputs as out:0, or sorry, out:1. But again, these are just labels that represent what port we have these plugged into. Right? And then out of our PLC comes out of common 1 or common 2. I don't have space, so I'll just put a general C. Right? This is all kind of inside of our PLC here. And this comes back to ground, or I should say more specifically, 0 volts, right? Okay, so this is our wiring diagram for our system. Now, it's up to us to program this system to behave the way we want it to, right? Now again, a very common pattern you'll see when working with start and stop push buttons is this guy right here, right? Once the start button has been pressed, the conveyor doesn't stop until the stop button is pressed. Right? We'll say our start is X1 and our stop is X2. So coming over here, got L1 over here, L2 over here. This is our outputs right here and our inputs over here. So again, as we discussed in lecture on Monday, there are kind of two ways of doing this. First is to use our latching mechanism, where first I'll start with a normally closed contact, right? Put my little things here to signify normally closed. We'll tie this one to X2, right? And if we look at our button here, right, X2 is normally open, which means by default it's a 0. If I press my button down, whoa, heavens. If I press my button down, right, the X2 bit changes from a 0 to a 1, which opens this circuit and cuts off anything down this line, which is what we want, right? For now, we'll keep it as normally closed. Next, we'll want to put our start button, right, which we'll leave as a normally open contact, X1, and we'll take these and route them into an out. Excellent. Now, right now, if I press my start button, right, if I lower this one here, whoa, heavens. If I press my start button, that energizes X1, so it turns the X1 bit from a 0 to a 1 when energized, right? That causes this guy to close, which means we have continuity, which will enable this output. But we can't simply put our motor here, because as soon as I let go of this button up here, right, as soon as I let go of my start button right here, this 1 changes back to 0, which would disable this, which would disable my motor. And we don't want that, right? We want our motor to stay on in the case that I let go of the start button, so we need a self-latching circuit. So for that, I'll use a coil, or C1, and we'll have an OR gate here. Right? Remember, OR gates run in parallel. I'll say this is contact C1. So now, when I close this guy, right, energizes my whole line. C1 here on the out is turned from a 0 to a 1. This guy detects that 0 turning to a 1, so it closes. Right? And now even if I let go of X1, we still have a path of continuity around this bottom branch, and C1 stays on until I turn X1 off. Right? That is to say, I push the button X1 to toggle this guy. Excellent. So we have C1, which represents our system is on state, right? So down here on my second rung, I'll say, okay, C1, I want to make sure my system is on, right? This condition must be satisfied in order for it to do anything else. And the first thing we want to do is simply turn on our motor, right? We come up here, we read, okay, once the start button is pressed, the conveyor doesn't stop until the stop button is pressed, right? C1 will be stopped when we press the stop button, right? C1 is our kind of on-off system. So now we're good to say we're going to turn output, and I'll come up here, double check, my conveyor is on, heavens, is on Y3. So we'll say, all right, I would like output Y3 to turn on when my system is on, right? And again, C1 is kind of our system on or system off. The final step here is to determine when our booting system, right, that little motor that kicks off the metallic object, enables, right? And I know, right, that I want some kind of output on Y4, since Y4 is where our booting is happening, right? That's the motor that boots stuff off, which is connected to Y4. So we want to control Y4. Now, reading through my problem statement, I'm going to go ahead and lay out the logical conditions where our motor here should activate, right? So the first condition, and this one is kind of coming from this area up here, is that we want the first condition, system should be on, right? And we've represented that as C1. So system, which is, or I should say system on, which means that C1 should be 1, right? All right. Our second condition is that something metallic should be detected, right? If something metallic is detected, the motor starts and boots the item off. So something metal, right? And if we come up here, we've wired our Hall effect sensor, right, represented by this guy right here, to X3, which means that X3 should also be 1, right? It should be on. It should be detecting something metal. Now we have one more condition here, right? Coming from this bottom paragraph here. The motor doesn't engage if a normally closed switch is overriding the setting. Now, the way I've worded this problem is a little ambiguous, right? I did not say if the switch being closed means the override is on, or if it's open means the override is on. So you may do this part a little differently, depending on how you interpreted this paragraph. I'm going to interpret this as the switch, as if the switch is closed, that means the override is on, and if it's open, that means the override is off. All right? So, right, looking at this condition here that we made, right, we want the override to be off in order for the system to boot something off of the conveyor belt, right? If the normally closed switch is overriding the setting, the motor doesn't engage, so we don't want the normally closed switch to be overriding the setting, which means this guy should be open in order to disable the override, right? At least that's how I'm interpreting it here. You may have interpreted it differently. This paragraph was a little bit vague. Again, we remember that when we open this guy here, that de-energizes this line here, meaning that X4 will be de-energized, or 0. So we want X4 to be, right? And again, we're saying that if it's open, the override is off. So if it's open, meaning that it's a 0, the override is off. So we want X4 to be a 0. Override off. Okay, so coming over here to our logic, right? Since we know these are the 3 conditions it needs to be satisfied, right? This right here is going to be one big AND statement, right? We want this one and this one and this one. So coming over here, right? We recall, all right, well, is AND a series statement or is it a parallel statement? If you said that it's a series statement, you'd be correct. Right? So we'll start with our first contact here. This guy is easy. Right? System is on. We just check C1. If C1 is a 1, that means our system is on. Next, let's tackle this second condition here. That is X3. X3. We want X3 to be a 1, right? So when X3 equals 1, we want it to be closed, right? And we remember between our normally open and normally closed contacts here, the contact that exhibits this behavior is a normally open contact, right? A normally open contact is a closed. Sorry, I'll start with open. It's open when the bit is a 0, and it's closed when the bit is a 1, right? So we'll keep this as normally open. And our next condition is the tricky one, right? We want X4 to be 0. That is to say, we want a system that is closed, or a contact that is closed when the bit is a 0 and open when the bit is a 1. We recall, right, the opposite of a normally open contact is a normally closed contact, right, that exhibits this behavior. So our next contact must be a normally closed contact, right? So normally, this guy here is closed, X4, and this guy then feeds into our out, right? And running through a quick sanity check, right? Let's say that I have my override engaged, right? So this guy here is making contact, right? My override is on. If my override is on, that means my X4 bit right here would be a 1, right? If my X4 bit is a 1, that means this guy opens, which disables this motor, right? Doesn't matter what these guys on, they can be opened or closed, but since this guy is forced to be open, since the bit is a 1, our Y4, or our booting motor, will never engage, right? Now, if I disengage my override, right, if I want to turn off my override, I want the system to behave normally, that is, I open my switch here, right? I open this guy. That means I cut off power to X4. If there's no power going there, X4 is a 0. We come down here. We say, all right, if X4 is a 0, right, that means it's closed, since we're using a normally closed contact here. So this guy stays closed like this, and that allows, right, under the right conditions, our system is on, and something metallic is detected, our booting motor to turn on, right? So zooming out, taking a final look at this, this right here is what our final diagram looks like. I'll zoom out again for the whole thing, just so you can pause and see this. This should also be posted in the course notes by the time this video is published.